So experiment 3 is uniformly accelerated motion. In this particular lab, we are looking at acceleration, or I should say motion, with acceleration where the acceleration is constant. We actually look at two specific systems. We look at the case of free fall, where an object is falling with no forces greater or approaching the size of the force of gravity, and the inclined plane, where we use, obviously, an inclined plane to decrease the rate of acceleration. Now, just a introduction here, since this is our first live lab, please read through the NJCU procedures with regard to COVID-19. Don't come to campus, obviously, with any symptoms, or if you've been in contact with anybody who has had symptoms. It's better that you miss this lab. You can take it at another time, and then come back when you're not at risk. Make sure you sanitize your hands on entering and exiting the laboratory. We'll have hand sanitizer there. Obviously, you'll be wearing a mask, but please don't touch your face. And if you do, please sanitize your hands after you've done so. At the end of the lab, we ask that everybody sanitize their station such that when we pick up the equipment, we're not risking any spread of the disease. Supplies needed. We provide the free fall setup, the inclined plane and cart, the lab interface, the computer. You might also want to bring a thumb drive so that you can save your graphs as they're generated on the computer. Now, the whole idea of this experiment is to study acceleration, but again, when acceleration is constant. So what we're going to look at is a velocity of an object moving under constant acceleration as a function of time. Now, we know that average velocity is the change in velocity with respect to the change in time. So if the acceleration is constant, the average is the actual acceleration. It's acceleration, it's the instantaneous acceleration, it's the average acceleration. It never changes, it maintains its value. So the whole idea here is to graph this, graph velocity as a function of time, get a straight line, then use the slope of the line to determine the acceleration. Now, in the first case, what we're going to do is actually show directly that not only the acceleration of gravity is constant, but also that it is nearly the accepted value of 9.8. All right? So to do this, we are going to use this little range finding device. It's a little device that sends off ultrasonic pulses. It's pretty much like sonar. And it will track the position of the falling object. Okay? As it drops, it sends this information to the computer. The computer graphs position as a function of time, and then uses the change in position as a function of time to calculate the velocity at any time. All right? So again, you're going to compare the acceleration of a free-falling ball to the accepted value of 9.8. Remember, the general goal of this experiment is to show the acceleration is constant, that the acceleration of gravity is nearly 9.8 meters per second squared, and that also acceleration is a vector. We'll get more into that at the end. So here we have the ball. You're going to hold it right under the sensor, and at the same time you release it, you're going to hit start on the computer. Okay? So it takes a little bit of dexterity because, again, due to social distancing, we normally have two people do this. We can't have that this time. So we're going to drop the ball. The ball is going to hit the table, bounce up, and then go into free fall multiple times. So every time it's in free fall, not hitting the table, you should get an acceleration close to 9.8 meters per second squared. Every time that it hits the table, obviously that is quite an acceleration because it's changing direction. Those moments we're going to actually ignore. So this is what it would look like on the computer. Down at the bottom of the screen, you have velocity as a function of time graphed here. This is the important graph. Underneath it, there's position as a function of time. And to the corner, you see that little record button? That's what you're going to hit as you drop the ball. Now again, you've got to be very careful here and make sure that as you drop the ball, you're right dead center underneath this thing, that you allow it to fall, and that the sensor is also pointing right, dead center to the table. Okay, so you hit this, let it bounce a few times. Once you have enough bounces, I guess you'd say, you'll hit the stop button, or if the ball rolls off the table, you hit the stop button. And basically, if we graph position as a function of time, this is what the ball should look like as it's bouncing off the table. Little parabolas, right? Okay? Now, these arrows indicate where the bounces take place. And obviously, we're not interested in that acceleration because that acceleration is not constant. We're interested in the acceleration while it's still in the air, while it's above the table. Now, to the sensor, it doesn't see position going up as the ball's going up. The sensor's looking down at the table. So the ball's closer to it, okay, when it's, basically at the top of its arc, and therefore the position is going to be low, and then the position is going to be recorded to be higher and higher as it gets closer to the table. So on the computer, what we get is these parabolas that are upside down instead, okay, or we get this image inverted over here, position as a function of time. And clearly we can see bounce, 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 everywhere it goes right there. Okay? As we go up here, our position is getting further and further from the sensor. Now up here, this is the important data because this shows velocity as a function of time. This up ramp indicates that the ball is in free fall. Okay? It's going through its arc. This steep line right here is an indication of the ball on impact. It happens very rapidly. So you get an upslope, that's the data you want. The downslope is the impact that we ignore. So you can see slope here, slope here, slope here, slope here, slope here. I've got quite a few different measurements that I can make. Okay? And the goal is going to be finding the slope of each of these lines on the uphill and calculating the acceleration from that. Okay? Now, how do we do this? All right. You're going to select all these regions where we're getting away from a bounce. We're going to basically select a few data points away from the bounce because, again, because of averaging, we want to make sure that we're not taking in a data point that was happening while a bounce was occurring. But I can see I've got 1, 2, 3, 4, 5, 6 really nice slopes for me to calculate what the acceleration is. Now, obviously the acceleration is downward once again because everything is pulled downward according to gravity. However, to the sensor is looking down. So to it sees the acceleration increasing as the ball's going away and decreasing a downslope when the ball's being pushed up toward it. So this sort of upside down world, the way the sensor's looking downward. Okay, so how do I get the slope? Now normally you would graph this on a piece of paper, you do rise over run, okay, after selecting enough data points and fitting a line through that, and that would be your acceleration because, as we know, the acceleration is the slope of velocity as a function of time. Now, what's nice about this is I can actually select this highlight tool, highlight the data points that I want, okay? And the computer will do an average for me. We'll actually find the slope or fit a linear slope to that, much better than I could probably do on a piece of graph paper. So I click on this little highlighter tool, a box will pop up, I'll then drag that box to whatever location that I want to measure. And again, see this upslope right here? I'll exclude a few data points where it goes down with the bounce, exclude a few data points where I actually held the ball before I released it, okay? And notice here, this M value gives me a slope. Here it says negative 0.0321. Now obviously this was not a ball being dropped. This upslope, okay, has been converted into a negative because the computer understands that the sensor is looking downward and that an upward slope would indicate a negative acceleration. Normally if we graph velocity as a function of time, the acceleration is positive if we're going up, negative if we're going down. Okay? So this slope, when I get this, should be right around 9.8. All right? I should get an m value equal to 9.8, close, plus or minus some uncertainty. That's due to the scatter of the points. So it does a little standard deviation calculation right there. These other factors aren't really that important. B obviously is an intercept. That's not really of relevance here. So again, I find the slope of this. The example I gave you is purposely not 9.8. You'll have to find the slope of your data. Once you have that, know that the acceleration of gravity is equal to the acceleration I get on here, which is equal to the slope. Really very easy to obtain the acceleration from this graph. Everything is done for you. And again, this was my first measurement right here, which I made right here. You're going to need 5 measurements. So maybe I measure here, maybe I measure here, maybe I measure here. If I don't get 5 nice lines on my one trial, then drop it again, and then that'll give you a set of more. Okay? So here I could actually get 6. This was such a nice trial that was done. I could have measured the acceleration here, 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 taken all 5 measurements, okay? Save each run that you do, however, okay? You don't have to save each measurement that you do, but at least let me see all of the different, acceleration of the different lines that you're using here, all right? So you want to save that graph, save the position graph too, all right? You can do a screenshot, you can save it on a thumb drive, you can probably email it to yourself, you can even take your cell phone and take a picture of the screen. But you need to preserve that graph because the computer's not going to preserve it for you. Once you leave the lab, this graph will be erased automatically. Okay? Very important that you take care of this. All right. Now, to get the average value, it's just the 5 slopes that you have, add it together, take the sum, then divide by 5, and that will give you your average value of the acceleration. This becomes your experimental value. Now you have to do percent error. The experimental value, which is also this average right here, minus 9.8, absolute value over 2, times 100%, gives you experimental error, and that'll tell you how successful you were in determining the value for acceleration. Okay? Let's go back here for a second, folks. Once again, what do we find out just from this first part? 1, the acceleration of gravity is constant for free fall. We can clearly see that the acceleration is constant because the slope is constant. 2, acceleration is a vector. It can be in the positive direction, it can be in the negative direction. Actually, it's reversed, but we can clearly see a positive slope and a negative slope indicating 2 different directions. Okay? Remember, to be a vector, even though this is one-dimensional motion because it's up and down, to be a vector, you have to have magnitude, the slope is the magnitude. And you have to have direction. Up, down, positive, negative. There's your vector nature. There's your direction. Okay, so do 5 different slopes, find the average, calculate percent error, and you're done with the first part. Okay. In the next part, we are going to use an inclined plane because that's what Galileo used to show that the acceleration of gravity was constant. Also, this is a nice setup to actually get a more precise measurement for gravity when timing is an issue. Okay? Obviously, the computer with this little position sensor, this range sensor, fires these pulses off every 50th of a second, so it can make a very rapid sequence of measurements. But let's say you're doing this with a stopwatch, you'd want to slow down the acceleration. Now, very important here, the acceleration of this car equals g times the sine of the angle. Okay? You're going to adjust the angle of the inclined plane. There's a protractor on the side. Make sure it's very precisely 5 degrees. Okay? A slight increase in angle is going to rapidly change the value of your acceleration. All right? So Be as precise as you can with a little protractor on the side. You can't see the protractor. It's actually on the other side of this whole thing, but it's got a little plumb bob that hangs, and then you'll see a protractor going from 0 to 180 degrees. Actually, I think 0 is straight down. But in any case, you want that at a 5-degree angle for your first run. All right? Now again, your acceleration should be g times sine theta. So you'll do 5 degrees first, then 10 degrees second for the next set of data. All right? This is your little frictionless cart. It has some friction that'll slow it down a little bit, but just like the falling ping pong ball, the amount of force from the friction is negligible compared to the force of gravity. Pull this up about halfway. Don't go all the way up the inclined plane, because if it hits the end of the inclined plane too hard, it'll bounce off and it'll come off the track. Here's your range detector. You've taken that off the stand, which is at the very top of the, you dropped the ping pong ball, it was at the top of the stand. You take that off and you slide it in at the top right here. You still leave it plugged in, you're still running the same computer program, you're just now facing the range detector down the inclined plane. Now, just like you had to adjust the range finder to make sure that it was pointing straight down, make sure this is pointing, parallel with the track. Okay. Once again, you hit the record button when you want to start. You're going to need to delete your last run. So there's a little delete last run button up here. You can also, I think, delete it from the top menu bar too. Sometimes this is the easiest one to use right here. But again, once you're ready to record, release the cart, hit record right before you release the cart. Okay, so sort of do a hit record and let go, just 1, 2, very, very quickly. Once the cart has gone far enough, you can hit the stop sign and do, obviously record that. You're going to do this 5 different times. So you could let it bounce a few times. This is up to you. Let it bounce off the end a few times and get that same sawtooth pattern that we saw by dropping the ball in this bouncing. Or you could do it 5 different times. This might be the easiest. Again, if you only allow it about halfway up, it's going to hit down here. There's a little spring plunger here. It'll bounce off the end, come back up, and it'll measure that velocity as a function of time, a few different times. And as long as you have enough, straight lines to measure, and again, here the slope is going to be much less than 9.8 because you're at a much lower acceleration. As long as you get enough, measurements, at least 5 measurements, you should be fine. Just another aside, the reason why your acceleration is so small is because of this equation. 9.8, is a fairly large number for acceleration, but the sine of 5 degrees is a really small number, okay? So don't expect to get a very great number here. We're really trying to slow down gravity using this inclined plane. So again, 5 different slopes are needed. If you need to drop, let the cart go more than once down the track to get additional slopes, that's fine. Just make sure you don't change the slope. Okay? Getting an accurate slope is so important here. Making sure that protractor is right on 5 degrees is essential. Your acceleration is not g. You'll get the average acceleration. Okay? Using the average acceleration, we can calculate what the experimental value for g is. Remember, the average acceleration is g times sine theta. We want to solve for the experimental value for g. It's the acceleration divided by sine theta. Sine 5 degrees is a small number, so that'll make your g much larger than the a was. Calculate the percent error. Here's your experimental value for g. Here's your percent error. We do the same thing again. We're going to go back, reset this. There's a little clamp up here that you're going to raise this end until the protractor reads 10 degrees. Do the whole thing over again. Okay? Always remember, save your graphs. Save all your graphs. If it's a screenshot, if it's whatever, however you're preserving this data, you need this data in your laboratory write-up. Okay. Now, just remember, you can have a few graphs for this. At minimum, you'll have 3 graphs. You're going to also have a table for 1 and 2 tables for part 2. Okay? So at least 1 graph, maybe more graphs for the free fall, 1 graph or maybe more graphs for 5 degrees, 1 graph, maybe more graphs for 10 degrees, and also 3 tables for your data. Okay? Make sure everything is labeled, everything has proper units. Okay, title, labels, proper units. All right? Again, when you're coming up with a conclusion, okay? The hypotheses to be tested. Gravitational acceleration is constant and equal to 9.8 meters per second squared. What's your proof? Your proof is these graphs. Okay? The proof is these graphs. If the slope is close to 9.8 for the free fall, you've shown the acceleration of gravity to be such. If your calculation gives you a g with the inclined plane, which is close to 9.8, again, you've shown it's close to this value. And just the fact that this is a straight line is showing you constant acceleration. How do you show that it's a vector? Here you have a positive slope, here you have a negative slope. Okay? When the ball changes direction, the sign of the acceleration, which is related to the slope, also changes. All right, very important. You're writing this up as a formal lab report. Okay? You're going to put this into a report on a word processor. If you need to import your graphs as graphics files, you can do that on Microsoft Word or other word processing programs. Make sure you have an introduction. Okay? What are you trying to do in this experiment? Okay? That was very closely laid out here, but put this into a paragraph. What is the theory? Obviously, you need to talk about the theory of how we calculate the acceleration by graphing velocity as a function of time, how it's a slope, put equations in there, back it up. The fact that the acceleration of gravity for gravity is 9.8 meters per second squared. The fact that acceleration is a vector, it is downward for gravity, okay, as direction downward, and a value of 9.8 meters per second squared. All that should go in the theory. Procedure is basically just how you went through the different parts. I'm going through the procedure right now, or I did. Results, present your results. Present your graphs, present your tables, but also explain what they are. If your results section only includes graphs and tables, you will get a low score. Okay? You must refer to each graph, describe what each graph is. Have a small paragraph describing each graph. Okay? In the discussion, discuss the significance of each graph. Okay? Fact that the slope was basically constant, was a straight line, what the importance there was. Okay? How your results agreed with basically what your expectations were. Conclusion, basically you're just wrapping the whole thing up. All right? What can you say from your results? Were you able to say the acceleration of gravity is 9.8 meters per second squared? Were you able to say that the acceleration of gravity is constant? Were you able to say that gravity is a vector? Post-lab questions include those below the conclusion. References, at least reference the lab manual that Dr. Pincus put together. Okay? You can also reference our textbook, because obviously a lot of these ideas are in that textbook. You're also going to be graded, each one of these are with 10 points. Some of them are longer than others, but so, like the reference, all you have to do is put a reference and you get 10 points. How easy is that? Finally, make sure it's in the correct format, because you can get hurt in more than one place if you leave out something. Okay? Everybody wants to put the results in the discussion together. Okay, you do that, not only are you going to hurt your results out of 10 points, your discussion out of 10 points, you gave me the wrong lab format. You're using a word processor. Spelling should all be correct. You can use Grammarly if you don't know about Grammarly to make sure your grammar is correct. And obviously all the units are SI, they're all meters per second.